All right. Hi guys, welcome to the channel. Don't forget to like. Sorry, never mind. I think this lesson is pretty cool. We're going to talk about some of the concepts we've been going over, and it's all going to come together in a beautiful picture known as a graph. Okay, we're going to be talking about graphing motion. There are two ways we can graph motion. We're going to do one way today, and then next week we'll talk about the other way. When we're talking about motion, we've talked about two ways I can measure motion. So if something's moving, I can measure two basic things about it. You remember things we've talked about in terms of what I can measure about a moving thing? Alex? The speed. I can measure how fast it's going, which would be, I could do the speed or the velocity, or kind of different ways of measuring how fast it's going. What's another thing I can measure about something's motion? We got speed, velocity, which are kind of similar ideas. Yes?
Distance.
Distance, which is how far something moved, right? So, or instead of distance, I could also measure its displacement, right? Distance and displacement both have to do with how far it moved. Speed and velocity have to do with how fast it moved, right? So two basic ideas. For graphing today, we're going to look at how far something moved, aka displacement. So we're going to be looking at displacement versus time graphs. Okay, we're going to be making line graphs, right? And I'm going to have two axes. Okay, what's the horizontal one? That's x-axis, and then I have y. Okay, on my x-axis, we're going to have time, which is going to be my independent variable. Have you guys heard about independent and dependent variables? One person has. Okay. We were supposed to go over this last chapter, but I accidentally skipped it, so we're going to talk about it again. All right. Okay. And on my y-axis, we'll put displacement, which is the dependent variable. Okay. We'll talk about what independent and dependent variable. Taking notes. Okay. So, in an experiment, the independent variable and the dependent variable both change. Okay, so I have time and I have displacement, and they're both changing, but what distinguishes them is what I do with them. Okay, this is my independent variable, this is my dependent variable. Okay, since we didn't cover this last chapter, my independent variable is the thing that changes on its own, or it's the thing that the scientist changes on purpose. In this context, obviously time changes on its own, right? I don't have to like turn a crank to make time move. But in other experiments, the variable on the x-axis could be something else that I am intentionally changing. The dependent variable also changes, but I do something else with it. I don't change it myself, I measure it. So the dependent variable is the thing that we are observing or measuring as it changes related to the independent variable. Oh, actually, Tori, I have a pile right here. Just throw it on the pile. Thanks. fun way you can remember which one goes where is if I have my graph with the x-axis, I can make a letter I. For independent variable goes on the x-axis. On the y-axis, I can make the letter D, which helps me remember that the dependent variable goes on the y-axis. So that can be helpful maybe. So the independent variable is the thing that changes on its own or is changed by the scientist. The dependent variable is the thing we are measuring or observing, which in this case is time and displacement. Still see lots of writing, so I can wait. Okay. I have 7 graphs I want to look at of different types of motion. Let's start simple. Let's say I'm moving forward at constant speed. I want to look at what would the graph look like. Okay, so my time is usually going to be in seconds, right? So every second I'm covering a certain amount of distance. Okay. Let's say I'm starting at a starting point. What's my displacement at the starting point? How far away am I? Super hard question. If I'm at the starting point, how far away am I? How many meters? 0. Thank you. Okay, 0. So we're starting at 0 displacement, right? And then when the timer starts, if I'm going constant speed, what that means is I'm going the same distance every second. Which means that this graph would look like a straight line, yes? So in this graph, in 1 second I go 2 meters. In another second I go 2 more meters. In another second I go 2 more meters, right? Constant speed means I'm going the same distance every second. We okay with this? On your notes, you don't need to put numbers or stuff. All I want you to know is the shape, okay? So on your notes, you can just make a graph, time, displacement, and just draw a straight line. Right now, I just want to focus on the shape of the graph depending on the type of motion. What if I was going constant speed, but going backwards? Cooper?
From the y-axis and go down.
I would be going down. If I'm going backwards, that means I'm coming back to where I started, right? I started far away, and I'm coming back to the starting line, so it would go down. But it's still a straight line because I'm covering the same amount of distance every second. So I went backwards 2 meters in the second, then I went backwards 2 more meters, then I came back 2 more meters. Constant speed, just a different direction. Yeah? Nice job with that one. That was good. Okay, we're going to do different combinations. Ready for the next one? We'll go forward. Next one. Let's say I'm going forward, but now, instead of going constant speed, I'm speeding up. So now I'm covering more distance, but every second I cover a further distance, and then I cover more distance in the next second. Then the next second I go even farther. Can we imagine what that graph would look like? It's not a straight line anymore. It's curved. in the first second, I covered 1 meter. And then in the next second, I went 2 meters. And then it looks like I went 5. And then I went 10 more meters. And then I went 20 more meters. And then I went 30 more meters. Right? If I'm covering more distance every second, then I must be speeding up. So this one's curved. What if I'm slowing down?
Opposite.
What is going to be the opposite?
It's gonna start high and go.
Maybe. So let's think about this. So what direction am I going? Forward. So let's say I'm starting at my starting point and I'm going to be going forward. So I'm going to be getting farther away. So I'm going to end up farther away. But at first I go really fast and cover a lot of distance. Then I cover a little less distance and then less distance and then less. It's going to curve like that. So if I were going to make a graph of a car in a drag race, right? It's sitting at the starting line. It gets the green light and it covers a big distance in 1 second, right? And then let's say it crosses the finish line. And so it's got to slow down, right? So it's slowing down. In the next portion, I cover a little less distance, right? And then after that, I cover even less distance, and then I cover less distance. Right? If you put your brakes on the car's still moving forward, right? So I'm still getting farther away from my starting point. I'm just covering less distance each second. Okay? So this is moving forward but slowing down. Cool? What combination do we need next? We're going to do all the combinations. Which one have we not done? There's 2 we haven't done. We've done forward speeding up, forward slowing down,
Now we need to
forward constant speed. We've done backward constant speed.
We need to go backwards again.
We need to go backwards, doing what? Speeding up and slowing down, right?
Yeah.
Okay, so let's do backwards slowing down. So let's say I start far away and I'm going to end up back at my starting point, right? I started far away and I'm going to back up to the starting point. Here's the question though. So a straight line was constant speed. Slowing down is going to be curved. But here's the question. Is it this or is it this? What do you think, Jensen?
Theoretically,
Top one or bottom one?
theoretically, it could be either one.
It has to be one of them. It can't be both. One of these is I'm coming backwards and speeding up. The other ones is I'm coming backwards but slowing down. What do you think, Cooper?
It's the bottom one.
You think it's this one? Can I have a vote for that one? Why do you think it's that one?
Because you're going at a fast pace and then you're slowing down as you go back.
Yeah, I'm covering a big distance, right? I start far away, I get really close, but then I get less close, less close. Yeah, it's exactly that one. Nice job. If I'm coming backwards but slowing down, the graph is going to be getting flatter. If I imagine this as like a cross-country race or something, let's say I started at the starting point and then started going backwards, slowing down. What would that graph look like? Can you go backwards from the starting line? Just like, is it physically possible?
Yeah,
It's physically possible.
It would be
Your displacement would be negative. So we don't have to start far away. If you do this and go backwards, you can have graphs that go into the negative region. So displacement can be negative, I'll just mention that, okay? So then the other way, we can go backwards but speed up, which is gonna be this one, right? Which I think is, for some reason, this one's negative. Also, these all say distance, they should not say distance. I made these like 2 years ago and they were wrong, so, sorry. I just haven't changed them. So here, I started at 0, I went backwards, I covered a small distance, then I covered a little more distance, then a little farther, 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 farther every second. So I'm speeding up. Is that all the combinations? Forward, backward, speeding up, slowing down, constant speed, did we do all those combinations? What are we missing? Well, we can combine them, yeah, but is there, like, we can do different ones at different times. I think we've done all the combinations. What if I'm not moving? Why do I have this slide twice? Okay, not moving. What would that look like?
You're just staying in the same spot.
Staying in the same spot, does time stop?
No,
Time keeps moving forward,
but you're not.
but my displacement
It's just as.
is a flat line. So if I'm looking at this graph specifically, I'm at 5 meters and I'm just standing 5 meters away from the starting point, right? Time is still happening, but my distance from the starting point, my displacement, is just 5, right? If they start the race and I just stand on the starting line, I would just have a flat line right here, right? I'm not getting any farther away. Cool. Okay, let's summarize what we've seen here. There's a few patterns I want us to notice. Some patterns that I think will be helpful. Look at all of your graphs that are moving forward graphs. What do all of the forward moving graphs have in common? I think there's 3 of them.
They're going in an upwards direction.
They all go up, right? If I'm moving forward, then I'm getting farther away from my starting point, right? The question is, am I going at a constant speed? Am I speeding up or am I slowing down? But regardless of my speed, if I'm moving forward, I'm getting farther away. So, moving forward, they all have increasing displacement. The graph goes up. What about my backwards graphs? If I'm moving backward, they all go down in some way. If I'm going down at constant speed, it'll look like that. If I'm speeding up, it looks like that. If I'm slowing down, it looks like that, but they're all going down. Yeah, it does. Or our coffee bean. Do we see that pattern? Okay. Now let's look at there's 2 graphs for speeding up. Look at your 2 graphs for speeding up. What did they have in common? They're both curved, but they both curve in a similar kind of way. Give me 1 minute. Let me finish this. Someone see it? There's 2 speeding up graphs on your notes. What do they have in common? They're going opposite directions because there's one forward, one backward. But if I'm speeding up, there's a common thing that the graph does. It curves what direction? One goes up, one goes down. We're looking at this graph and this graph. They both curve, they're going opposite directions, but what are they both doing? my mind?
Going away
Yes.
curving away from the x-axis.
They are curving away from the x-axis. Are they getting steeper or flatter? Steeper or flatter? Right, if I imagine there's like a ramp, that's pretty steep, and then this is also getting steeper, yes? They're getting steeper in opposite directions, but they're both getting steeper. If I'm speeding up, the graph gets more steep. It gets more vertical. If I'm slowing down, I either have this graph or this graph. Markers are sad. This one or this one is slowing down. What do those graphs have in common? They're getting, say it loud and proud, Allison. Flatter. The graph is getting flatter. Oh, I can't type. The graph are getting flatter. Graph getting flatter. If you're slowing down, the graph gets more flat, or it gets more horizontal. Yes? See if you can go. Okay. Questions about any of this? Okay, I want us to practice recognizing how to look at a graph and interpret it to understand what type of motion is happening. Okay, let's do some practice. On your notes, try to make your own graph that has these three things happening in that order. Try to show a graph that has these three things happening in this order. We got it? If I'm going forward, constant speed, what does that look like? Straight line, then I stop. So if I stop, time keeps moving forward, so I have a flat section. And then if I speed away, then it curves getting steeper, right? So this is my constant speed, is gonna look something like that. If I stop moving, time keeps going, so I have a flat section. But then if I speed away, the graph should be getting steeper. Make sense? I'm walking down the street, constant speed. I stop to tie my shoe, so I'm not moving. And then a dog jumps the fence and starts chasing me, so then I gotta speed away and get faster as I go. Right? So you can make a little story out of your graph if you want. You okay with that? Skip this slide. Okay, last thing I want to talk about is slope. I want to look at the slope of these graphs and see if the slope means anything for our graph. Okay, what is slope again? That's how you calculate it, but what does it mean? If I say like this graph has a really high slope and this graph has a really low slope, what am I talking about? Can you show me with your arm? If I had a really high slope, what would that graph look like? This. If it had a low slope, what would that look like? This. Or I could even go negative. So what am I describing when I say slope? What am I trying to describe about the graph? On some graphs, but just in general for any graph about anything, slope would be how, read my mind, starts with an S, rhymes with
Steep.
Steep. It has to do with how steep the graph is, right? If I have a high slope, I have a really steep graph. If I have a low slope, I have a very flat graph. Yeah? Okay, so we've got time and displacement. Slope is the steepness of a line. Calvin said that if I want to calculate slope, I do rise over run. What does that mean? Right, I go up so many on the y-axis, and then it goes over so many on the x-axis. Okay? Another way I could represent that is with these symbols here. Delta y divided by delta x. Yes, I know it's a triangle, but it's also a Greek letter. That's a Greek letter called delta. What does delta mean in math world? Anyone know? Yeah?
Delta arrow.
No. In math world, delta means change. So this is the change in the y-axis divided by the change in the x-axis, which is my rise over my run. Okay? Different ways of saying it. Well, hold on a second. If we're looking at this specific graph with displacement and time, what is on the y-axis? For what we're talking about today? Look at your notes. What's on the y-axis? Displacement. Displacement over time. So delta y over delta x would be the change in displacement over the change in time. Wait a second. Displacement over time. Distance over time. That sounds familiar. What's distance over time? What? Speed.
Yeah.
Or the velocity. Oh my gosh. So what we're saying here is the slope of the line equals the velocity. If I can calculate the slope of the line on this type of graph, that is the velocity of the object. Kind of crazy. On a displacement versus time graph, the slope equals the velocity. It's kind of nifty. Someone's got a phone. Do you need, is it in there, or Jensen, do you need to turn it off?
I don't have.
I'm not going to take it away.
It's in there.
May I-
It's in there. If it was you, I'd just ask you to turn it off.
May I see if it is mine?
Yes.
It's in there.
Cooper says it's in the other room.
It's in there.
It's
Okay,
in there.
well then don't worry about
It,
Okay.
it sounds like it's from the
Because
other
I know
one.
mine.
Okay,
I
I'm
know
not.
mine is shut off.
The webs we weave. All right. Anyway, okay. Side note before we're done. Can you have negative slope? Is that a thing on a graph?
Yes.
So you can, right? Negative slope means that it's going down, right? Can you have negative velocity? Is that a thing? We literally talked about it yesterday. Remember the train and the elevator?
Yes. You can have negative.
You can have negative velocity. What does negative velocity mean? We have forgotten everything.
It means you're going backwards and to the left or down.
It means you're going backwards or down or to the left. So negative slope means negative velocity, which means backwards. Wait a second, look at your graphs. What do all the backwards graphs have in common?
They're going down.
They're going down. they have a negative slope. Oh my gosh. It all fits together, right? If I have a graph with a negative slope, according to this, that means I have a negative velocity, which means my graph is going to be going down, which means it's going backwards. All of these ideas fit together in this graph. Mind blown. I think it's kind of cool. It all fits together perfectly. Negative slope, negative velocity, moving backwards, graph going down. Positive slope, positive velocity, moving forward, graph going up, right? All of these ideas fit together. Cool? All right. We have a short amount of time, so how about we do a short worksheet? I can give you the long worksheet, because I got two. Or should we do the short one?
The short one.
We'll do the long one tomorrow.